Anujan S talks on refinery technology, which include processes, process equipment, and also oil economics.
Friends, in this episode we will see a simple method to do some fine tuning of the PID controllers in the process control system. You appreciate that the controllers, when they are put on auto mode, takes action depending on the error prevailing between the set point and the process variable, and also the values of the proportional, integral and derivative constants assigned for that controller. So these PID tuning numbers, they are essentially responsible for fast action, robust action of the controllers. What people mean by robust action is when you make a change in set point, without much delay the PV also should follow. There should not be any much oscillation, and ultimately there should not be any offset remaining between the PV and SV. This can be done with the help of a lot of software available in the market right now, which requires data collection from the DCS through a software which is sitting on a supervisory computer or a connected PC. Without the help of a software, now we will see how a simple system can be tuned. This method is available from the ControlSoft incorporated software, and we will see how it is being done. Now, first you have to do an offline tuning with the help of a initial settings. Now, normally all the PID controllers will come with a factory setting of maybe some proportional band of proportional gain of about maybe 50 and integral of about 100, 200, but that will never work. So you have to change those numbers. So you have to have an initial setting done, for which you require maybe a test by a Siegel-Nicholas method, which is giving a perturbation or a change in the set point at least by 5 to 10% of the MV value, and then watch the response, collect the data and analyze to yield the proportional, integral and derivative settings. This is slightly cumbersome, and without any data collection this will never work. Data collection software will never work. So we will go by some other method. Normally when you start a license unit from major licensors like UOP, their technicians will come for commissioning the plant. So they will initially provide the set point, the PID values for all the controllers. Here I am using the proportional, integral, derivative time constants for all the type of controllers, and this is the one which UOP has been using. Now this chart, this table gives the proportional, that is the gain, and integral time in minutes and derivative time in minutes for different type of controllers. That is the flow controller, level controller, boot level, liquid pressure, gas pressure, fuel gas pressure, heater temperature and column temperature. These could be set, but only thing is that you should understand that you have to take care of the type of DCS which you have. Some of the DCS will have, instead of gain, proportional band, and some will have a different value of the integral time and differential derivative time. If this is in seconds, assume that your integral time is in seconds. If I have a 0.1 minute means it is 6 seconds. You have to correct it accordingly and key in the values. So this provides us the initial setting of all the controllers. Please bear in mind you have to change the factory settings, otherwise none of the controllers are going to work. So with these initial settings, the controller will almost be working with some oscillations and all, but with the method provided subsequently, you can fine tune this controller and make it robust. What you do here is put the controllers on auto with these settings. When you put on auto and then make small changes and observe the response. There are 5 pages given after this. After every change the PID settings and you put make a change, you see which of the 5 pages given are relevant and make the corrections. And you do it a couple of times. Ultimately you are, and just wait till you are perfectly satisfied with the performance of the controller. When you see that after making a change, the response is delayed by this value. It doesn't start off with the change of MB and then it goes slow and then it doesn't, there is an offset ultimately. What you do is the gain has to be multiplied by 1.5 times. So the new gain is 1.5 times of the original gain. If this starts immediately with the change in set point, but there is a huge overshoot and it sustains, then your proportional gain has to be reduced to 50% and integral time also has to be reduced by 50%. Now this takes off immediately, but the overshoot is tolerable, right? But overshoot is there still. In that case, your gain has to be made to 80%. So reduce it by 20%. Integral time to be reduced by 50%. If the peaks are continuing more than 3, then integral time has to be reduced to 50% and derivative time has to be increased by 50%. Can you notice increase by 50%? And the last one is if the offset is sustained, integral time has to be multiplied by 2. So all these 5 steps you see which is relevant for this particular context, make that change and then again make a set point change and see the response. So by doing it 2-3 times you can properly tune the controller. You don't require any data collection software, no supervisory controller, no nothing, just your DCS panel. So probably this can easily be used by operating personnel sitting on the DCS panel, and then this will make their life much more easy because any upset in the plant can be easily handled by a properly tuned controller. So the life becomes easy and the plant can be shut up, shut down and then stabilize faster if you have a properly tuned controller. Thank you.
Before signing off, I have a few requests. If you like this video, please press the like button and also share this video with your friends so that they also can be benefited. If you have any comment on this video, please drop a line in the comment section just below this video so that I can try to incorporate in the future versions. Also do subscribe to my channel so that you get immediate notification whenever I upload similar videos in the future. Thank you.